All right, let's start the lecture here. Okay. So we started the discrete linear optimal control in the previous lecture. So just to quick review of the idea of a linear quadratic optimal control here. So basically we're trying to minimize the cost function at here. And the cost function is given in a quadratic format, so j equal to 1/2. Okay, the final state. So n at here, this is the final, basically final step. Okay, and then x of n, basically the final state. Everything is in a quadratic format. Essentially, it's like an energy type of a function. So you're trying to minimize this energy type of function here. And this is subject to the constraint, which is the original system state equation, right? And what we do is we use Lagrange multiplier and then introduce a Lagrangian function. We call that JA. So essentially, we combine these two equations together using Lagrange multiplier. So there's 1/2 at here. And then plus okay, so that's basically the Lagrangian at here. So a bigger bracket includes everything. Okay. So the original constraint problem can be simplified into an unconstrained problem for this function JA at here. Right. So now what we do is we just need to find the critical values or stationary point, okay, for this JA such that it's a minimum here. And all we do is basically we calculate the gradient of this function JA and then let it equal to 0, right? And that basically means we calculate 3 partial derivative. And the first partial derivative is the partial derivative JA over the control input U. And this let equal to 0. This gives us a equation this gives us the first equation at here. And the first equation is called control equation because this equation equal to 0, and we'll see that So basically we can solve for the control input u at here. So that's control equation. Second partial derivative, let's say we take the partial derivative with respect to the Lagrangian multiplier, okay, yeah, and let it go to 0, and we get, essentially we get back our constraint or the system state equation at here. And this equation, we call that, of course, it's a state equation, right? So this is our original state equation. And the last partial derivative is this partial derivative back to the x of k, okay, or the state, okay, and then let it go to 0. Now for this one here, I wanted to go over a little bit the details of how this result is obtained at here, okay? Yeah. So let's go back to this Lagrangian function. This is the Lagrangian at here, so it relates the constraint and the cost function together. Okay. Now, before I write down the results for this partial derivative, so what we can do is I'm gonna expand this whole term at here. Okay, so basically you see this k start from 0, right, and then k equal to 0, 1, 2, 3 until capital N minus 1, right? Okay, so the JA term, right, you have the first one is 1/2 x transpose, which is the final state, and then plus, okay, so I'm gonna write this out now. Okay, so let's see, starting from k equal to 0, then you substitute 0 here, 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 and then this is 0 here. This is a lambda to the lambda of 1, right? Yeah. I'll just actually I don't need to write this one here, but you just have to know if I let k equal to 0, what you're gonna get, right? And the k up to, let's say, so basically you have lots of terms. This is when k equal to 0, 1, okay, like this, right? Up to what? Up to the next term, I'm gonna write, let's say the next one here, I'm gonna write when k equal to k minus 1. Okay, so at, or just let's say at k minus 1 step. Okay, so basically you're going from 0, 1 until k minus 1 step, until k step, until finally which step? N minus 1 step. Okay, yeah. So that's what I'm trying to say. At this k minus 1 step, so what I'm gonna get? So basically, when k equal to k minus 1, what do? You replace that. Okay, you replace that k with k minus 1 plus u also k minus 1 r u or k minus 1. Okay, right, that's this term right here. And the next one, we're going to replace this k with k minus 1. So k minus 1 plus 1, you get what? K, right? Get a k out of here. So the index for this term is lambda k transpose times x k minus g x of u k minus 1 plus not plus minus h u of k. Right, so this whole thing out of here is when k is at the steps is at the k minus 1 value. Okay. That make sense? Okay. So now I'm gonna write one more out of here, which is at k steps now. General, right? K steps. Okay. So at these k steps, what do? I just basically everything's k, so bring everything down over here, right? So You get 1/2 x of k transpose here q x of k plus u k r u k minus not minus 1 plus u of k, and then plus this finish the bracket here, lambda transpose k minus 1 k plus 1 x k plus 1 okay, right? So that's your k steps right here, right? The k steps. And you're supposed to keep going, basically. You're supposed to keep going up until, right, k equal to n minus 1 step, right? Yeah. And then you can write down that, but that's not necessary because I'm going to take a partial derivative, okay? Yeah. See, this is basically what JA is, right? If you expand everything, you get a whole bunch of so many terms, basically. That make sense? Yeah. Now, for the third step, we're taking partial derivative of this function, right? This whole function with respect to what? With respect to x of k, right? So the k could be any number. It could be 1, or it could be 2, or it could be 3, right? It could be any numbers. But general number is k, right? General number. So if you look at the partial derivative, the gist of partial derivative is, if you're taking partial derivative to the k, then any other term, basically you consider what? As if they are constant, right? So then the partial derivative of this term with respect to x of k is 0, right? So now we just have to look for anywhere that has the term with a k term, right? So here you have x of k, and here you have xk here, and then of course here you have xk, right? So that's the only place you have a few x of k terms here. So you have xk over here, xk over here, x of k over here, right? Yeah. Every other terms, they're all considered as constant, right? Because they're not x of k terms, basically. They're not a function of that. So then you look at the results of partial derivative of JA with respect to x of k. All I'm going to concern is this lambda k times x of k. This 1/2 of this. And then lambda k plus 1 times g times this, right? That's all you need to concern. And using the simple, the fundamental, basically, matrix calculus, for the first one, when you take a partial derivative with respect to x of k, for the first one in here, what you get, so what you get is, what do you get? You get basically lambda of k at here. Okay, you get lambda of k. So when you take a partial derivative for matrix here, it's like a, basically, what's the derivative of 2x? You get a 2, right? But this is a matrix at here, so this is transpose. Then after the derivative, and that transpose is gone. So for the second one here, this is 1/2 x transpose qx at here, and that derivative you get plus. Just a second here. Where's my sign here? Where's my sign here? Second here, let's just double check. Sure. So sign difference over here. it's just actually, I think just a small modification in here, okay? Small modification. Just want to be consistent with my lecture notes right here. I'll add a negative sign right here. This basically negative this plus plus. It's still the same thing, okay? Yeah. So when you take partial derivative with respect to lambda right here, okay? So we got still the same constraint in here. Okay, so instead of this minus this minus this, it's a negative this plus this plus this. Okay, just want to be consistent with my solution for the lambda here. Okay? It shouldn't make any difference. Okay, so then what's the implication for my writing it here? Okay, so the writing here, this is negative plus plus, this is negative plus plus, right? Okay, yeah, that's the only difference right here. Right? So now if I look at the partial derivative with respect to x of k, so the first term is negative lambda, right? Got negative here, and the second term here is positive, basically q times x of k, okay? And the q is a symmetric matrix, okay? Symmetric and positive definite matrix. And then you have this term at here, and then plus another one, so g at here, so it becomes g transpose times lambda k plus 1. Okay, yeah, that's good. And this term, then this equal to 0 at here. Okay, so that's consistent now with what I have here. Yeah. So good, right? So the third equation, this is called a joint equation here. Okay, so this equation is called a joint equation. So the rest of the work is we're going to manipulate the three equations that are here, trying to find a solution for our control input u. Okay, the rest of the basically it's all about the algebraic manipulation of her matrix algebra. Okay, okay, so let's, as I said, consider the first one, equation 1, 2, 3, like this. Okay, yeah. So let's just be careful here. So now, from equation number 1, okay, so equation number 1, the control equation, okay, this is a control equation right here. I'll solve for the u at here from equation 1. Solve for u basically means move this term to the right side and then take an inverse of the matrix R, and then you get the solution for the u, right? Yeah. So solve for u, we got u of k equal to negative R transpose R inverse H transpose lambda k plus 1. Okay. I'm going to call this is equation number 4. Okay. Yes?
Sorry, just on your equation 3 there, could you look for yeah, you have that q times xk, right?
Yes.
In the term it's like x transpose k q times x.
That's right.
So when you take the derivatives, then
that's right. So
should it be like transpose?
So basically here is the general here. So if you take when you have a quadratic type of format like this, and then you take a partial derivative with respect to x, okay? Yeah. Now, if the A is a symmetric matrix, then the partial derivative of this one end up to be 2a times x out here.
Okay.
Yeah. So A has to be a symmetric in order for this to be true. If it's not symmetric, you get basically ax times A transpose x, that kind of things. Okay.
Okay, but
Yeah.
then I thought that the 1/2 was gone.
Yeah.
Especially because they multiply.
That's right. So 1/2 times this 2, then it's gone, right?
What about the other terms? Like
This term there's no 1/2 out of here.
oh, right. Oh,
Yeah.
Oh, I see. Oh, yeah. Oh, okay.
That's right. Yeah. As a matter of fact, you know, this is actually a very good point, because the next topic, when we finish this part, we're going to look for the actual minimum value for this cost function j. Okay. So back to your point, the lambda here. There is actually no difference if I put a 1/2 over here. Right? No difference, because why? the lambda is just a Lagrange multiplier, right? So if I put a 1/2 at it here, then I could just call 1/2 lambda to be d, right? Or it's a different symbol basically, right? It's still Lagrange multiplier basically. Does that make sense? Yeah. So sometimes this is actually, so you back to the Lagrangian in here. So sometimes a different format of this Lagrangian is, so instead of a 1/2 just over here, you probably see 1/2 for the whole summation sign in here. Okay, yeah, which actually make no difference at all. Okay, yeah. So, but for the next step, actually, I'm going to slightly change. I'm going to 1/2 over here, so you'll see that. Okay, but for now, let's just use this one here. Okay, so I'm going to get rid of this 1/2. Okay, so that's equation number 4 here. Okay, that's a control equation. Now, if you look at this equation right here, as a matter of fact, you see the equation here. This is very much like a u of k equal to negative times x of k type of form, except we don't see x of k here yet, right? Yeah, but that's the purpose, right? The purpose is we want to derive for u, which is equal to a negative k times x of k. But it's already in that format. There a negative sign show up already, right? Yeah. It just there's no x of k yet. Okay. So that's equation 4. And from equation number 2, okay, from equation number 2, of course we can solve for our state equation, and that's our state equation. Still call it equation number 5. Okay. Yeah. So state equation is what you have basically. Finally, from equation 3, okay, and equation 3 is this particular equation, okay, this particular one. I'm going to solve for lambda k based on this equation right here. Okay, so solve for lambda k, and I got lambda k equal to G transpose lambda k plus 1 plus q x of k. So I'm going to call this equation number 6. Good. Okay, so now we're going to work on this 4, 5, 6 now at here. Okay, work on the 5, 5, 6. Before we move ahead from 4, 5, 6, let's go back to, I'll let you finish writing it here. Okay. So far so good. Okay, so let's go back to the Lagrangian in here. Okay, go back to the Lagrangian. There's one more partial derivative actually we still need to write it down. So we have taken partial derivative with respect to u lambda x already. So let's last one. Let's take partial derivative with respect to the last state x of n in here. Okay. So one more partial derivative. So partial JA over this partial x of n in here, and of course that equal to s times x of n, right? Like this, and so let's move back a little bit here. Okay, basically the question is where do we see the x of n in here essentially, isn't it? Right? Where do we see the x of n? So technically speaking, you have x of n at here, but if you can look at this one here, when k equal to n minus 1, what's the last term? It's x of n, and then a lambda of n, and then it's here is what? X of n again, right? So technically speaking, you have two places. So last step here is lambda n at here. Should probably write down lambda n at here, and then times negative x of n, and then minus the rest of the term, right? So you do have another term containing the x of n at here, right? So you have the first term with x of n, the last term with x of n. So when you take a partial derivative, the last one you get here is minus lambda n, okay? And then this one equal to 0. So that gives us lambda n equal to s times x of n. So that's the results when you take a partial derivative of this cost function with respect to the last state vector x of n here. So this is what we get. This is very important actual results here. We rely on these results. So let's take a look at a little bit in-depth understanding of this one here. What do we want? So we want this state x of infinite, or at when k goes to infinite, we want this term go to 0, right? That's regulation problem. Basically, you want to regulate back to 0, right? Okay. If this term go back to 0, basically means even you time this s right here, it'll be 0 basically. Okay, so it'll be 0. Or in other words, your lambda at infinite should also be 0. Okay, should also be 0 here. Is that good? Yeah. And second of all, okay, if this k really goes to infinite, right? If k really goes to infinite, so in other words, if k goes to infinite, basically the cost function at here, this is not going to be infinite here, right? Yeah. And this is not going to be a finite step right here. Then I really don't need this term at all, right? So because it's going to be 0, right? Yeah. So your cost function when k equal to 0, then you don't need this term right here. Okay. And as a matter of fact, that's what we call the infinite horizon, basically, when k goes to infinite. So when this equal to 0, then no need for this 1/2 x transpose n and s x of n here. Okay. Okay. So now for based on these results headed here, okay, based on these results headed here, there is in 1975, okay, there are two authors basically, okay, in the control area. Okay. So they proposed a so-called sweep method. Okay, sweep method here. So essentially, by looking at these results here, so then the assumption here is, let's assume the lambda k. Okay, so you look at this, since the result tells you lambda n equal to s times x of n, then can we assume that the lambda k equal to pk times x of k? Okay, so that's essentially what this sweep method here is, trying to make a general assumption that any other k value, right, and lambda k maintain a relationship with x of k by multiplying not a constant matrix but a varying matrix P at here. Okay, so that's the assumption of this made here, which is called the sweep method. Now, if you make this assumption at here, then technically speaking, if I replace the k with n, right, we replace with n at here. So as you can see, at k equal to n, this matrix P at n should equal to what? Should equal to the S function, right? S function. Not a function. S matrix. Okay. And S matrix is something that you give at the beginning, right? You define the Q, you define the R, and you also define the S, right? You define them as certain, basically, positive, definite, and a symmetric matrix. That's what you define. So you have this S set here, okay? And the last of all, okay, another thing we also need to bear in mind is for finite step, okay, if you are at the last step now, so you're let's say you've controlled, finite step is not the most general one. In most of the cases where we're controlling is the infinite step here, which is the next will naturally extend the results to the infinite steps here, okay? But let's say you're considering this case is a final step. So at k equal to n, essentially we are at the last step now at k equal to n, right? That's it. That's for the control idea. At the last step, that's it, right? You don't apply any control anymore, basically, and you're done, right? Then, which means, okay, at k equal to n here, I shouldn't concern myself anymore with my control anymore. So any control effort. So the control value u at k equal to n should be 0. Okay, should be 0. Is that good? Yeah. Okay. So now let's, based on this assumption, okay, based on this sweep method assumption at here, and let's see what's going to happen to our equation 4, 5, 6. Okay. First of all, let's go back to equation number 4 at here, right? Go back to equation number 4. So we assume that the lambda k equal to p of k times x of k at here, right? And if this is lambda of k plus 1, so what do we do? Right. So now for equation 4, it becomes u of k equal to R inverse, negative R inverse, times H transpose, and then what? P of k plus 1 times x of k plus 1. Right? Yeah. So that's purely based on the sweep method, right? So you replace lambda k plus 1 with p of k plus 1 times x of k plus 1. Okay, and then x of k plus 1. We have it, isn't it, right? Which is what? Our state equation. Or equation number 5. Okay? Yeah. That's your u. So now you see, it's very close now. We got our x of k showing up in this expression now. Okay. So I'm going to manipulate now because I got u at here, I got u at here, and I'm going to move everything into one place, okay, and then take out the common terms. Is it okay? Yeah. So how do you do that? You multiply r, say r for both sides of this equation, okay. Then this r times this becomes a unity matrix, right? And then you're only left with this one here, okay. Yeah. So now you get R u of k equal to negative H transpose P times G times X. Expand it, okay? Let's expand it. Then minus H transpose P times H times U. There's a lot of symbols flying around here, but still the very fundamental matrix multiplications in here. Okay. Then I'm going to move this term to the right side here, so we get R plus H transpose P k plus 1 and H U of k equal to negative H transpose P k plus 1 times G x of k, right? That's right. So then you inverse this thing here to the other side. So what do we get? We get a u of k equal to, keep the negative, right? Negative R plus H transpose P k plus 1 H inverse, and then H transpose P k plus 1 times G x of k. Okay. And this is great because this is exactly in the format of what we're looking for, isn't it, right? And that is like the feedback gain matrix K, right? So negative something times x of k. Okay. Yeah. As a matter of fact, this whole chunk right here, right, is called the optimal gain expression. Okay. This is basically the optimal gain expression. Okay.
But now it
changes every step. That's right. And what does this depends on, right? You see, it depends on R, H, T. But then there's one more thing here. Depends on this P matrix here, right? Yeah. Which we don't have it yet. Okay. Yeah. But we got a solution for K, right? For now, at least. Okay. So let's keep using. We haven't solved all of the equation yet. So we have 4, 5, 6, right? 4, 5, 6. We use 4 and 5 now. We haven't do anything with the 6 yet. So let's do something with the 6. Okay. So for number 6, we're going to replace the lambda. Okay. We're going to replace the lambda with this sweep method, which is this one here. So we're going to replace the lambda with this. Replace the lambda k plus 1 with pk plus 1 x of k plus 1 here. Okay. And keep everything as it is. Okay. Yeah. So let's take a look at the way how equation 6 will look like now. So equation 6 becomes p of k x of k plus, not plus, equal g transpose b k plus 1 x k plus 1 and then plus q x of k. Okay. That's what equation 6 will become, right? If we apply the sweep method assumption. Okay. At the same time, we will do the same thing. This x of k is basically your gx of k plus h u of k. And then plus q x of k. Okay. Does that make sense? Yeah. Okay. So up to this stage, you look at this whole this equation 6 here. We got x of k here, x of k here, x of k here. The only one is the u of k, right? What's u of k? Look, we got our u of k over here. It's just getting longer and longer here. So, right? So we're going to replace this u of k with that whole expression. So imagine your head, you don't have to be stressed by this long expression. But you see, you got x of k here, x of k here, and then once you replace the u with this, you got what? You also got an x key here, right? And then you also have another x key here. Does that make sense? So basically, the whole expression, every term has a common factor, which is x of k, right? Yeah. So all I need to do is I'll bring everything to one side and take out the x of k, and then you have a huge expression in front of this x of k, right? And that expression is this. Okay, yeah, that's that expression. Okay. So you have this long bracket times x of k equal to 0. Then in order to satisfy this equation at here, so you have two choices, right? One choice is you let this guy to be 0, or the other choice is you let the whole big bracket equal to 0. Okay? But you can't have this one to 0. This is a, it's not guaranteed to be 0, right? So your only choice to make this one to 0 is what? This whole thing equal to 0. Okay? That's your only choice right here. Okay. And this whole thing equal to 0. I'm not going to rewrite it. Okay, so you can rewrite yourself. So I'll call this equation 9. Okay, equation 9 equal to 0. Okay. Yeah. Now this is this very important equation actually for you who has learned. Yes. Yeah. This one here. Oh, yeah, you're right. There shouldn't be k plus 1 here. It's a p. Yes, I missed the p here. Very good. Excellent. Yeah. Yeah, you do have a G transpose p at here, right? Yeah. Excellent. Yeah. Yeah. Someone's being awake. So this equation equal to 0, or this whole thing equal to 0, okay? This is called backward, okay, discrete Riccati equation. Okay. This is called a backward discrete Riccati equation. So it's like a DRE in short, so DRE, okay? And if you have a taking modeling control, when you learn continuous in a continuous system for optimal control, you actually have a similar equation. It's also called Riccati equation, right? But in our case, we got a discrete Riccati equation. Okay, yeah, and it's backward because you see here, you see this equation here. This is p of k minus a whole chunk of things at here, right? So that equation 9. And I can write it as p of k equal to, move all of these negatives into the one side here. So basically you get, I guess I said I didn't want to write, but I guess I need to write it one more time. Actually, there's one more thing here. This is not transpose. This is just h at here. Here. Just h, yeah. Okay. So that's the backward discrete Riccati equation. So you can see the left side is k and the right side is k plus 1, right? So it's a difference equation, first of all, right? It's a difference equation. And our typical difference equation is always okay, y of k plus 1 equal to something is all about the past values, right? But this is a backward. Okay? This is backward here. Okay? Now this backward here, you can still solve it. Okay, I'll show you how to solve it. So equation 9 solution basically gives this p of k. Okay? So the backward Riccati equation will give us the matrix P. Okay, the matrix P. And once you have the matrix P, you can see you plug it in here, you'll get this control gain of K, right? Yeah, so that's the connection. So this equation here plus that equation here, two equations basically give you a solution for this optimal control input U. Okay? Yeah. So in my lecture notes, okay, and I have also showed you a different basically variations for this discrete Riccati equation here. Okay, so let me show you a couple of differences at here. But in linear algebra, they're all the same actually. Okay, they're all the same. Yeah, so I'm gonna copy some of the things in here. Okay. So first of all, you see this one here, these results, right? These results that are here, it's very much like what I have just written here. Okay, so that's a discrete Riccati equation. That's one way how it looks like. It's one way how it looks like. Okay. And you could also see here, you can also, and I can show you why, but if you're interested here, okay? If you're interested, I can show you how this is obtained. It essentially, it manipulates linear algebraically, and you'll be able to obtain a slightly different expression for this discrete Riccati equation, but the same equation still. Okay, you see here, you could be this, or it could be this. Okay, all of them talking about the same thing basically. Okay, yeah. So,
why would having using different ones help?
Really, they're the same. If when you're using MATLAB to do the calculation, right? It really makes no difference at all. Yeah. It just the way I want to put it here is because different textbooks sometimes shows a different expression for the discrete Riccati equation, right? And for myself, I wanted to make sure they're the same, right? So I had to prove them, which I don't want you to prove, but just in case you see a different ones, right? Yeah. When you program, you can choose either one of these. They're all good. Yeah. Okay. Yeah. So you can see how do I solve for P of k then, right? Because it is backwards, so when you solve for them, you also have to backwardly solve it. Okay. So basically, which means remember that sweep method. So I mentioned it here, the sweep method here. When you use the sweep method, basically means at k equal to the last step, the matrix P, which is the solution of the Riccati equation, P of n should be the same as the weighting matrix S, right? So for this equation and here, right? For this equation, any of the equation here, so we solve it backwardly. So here is the last step, P of n equal to S, right? P of n equal to S. Then I'm going to substitute this P of n back over any one of the equation over here. So if this is n and here, then this is n minus 1, right? Yeah. So substitute S over here, okay? And then you solve for P of n minus 1, okay? Once you get the P of n minus 1, then you solve for P of n minus 2, and up to the last one, P of 0, okay? That make sense? Okay. So I'll show you an example. Okay, show you a simple example here. How does this the optimal control works? Okay. This example is a simple example, so we're going to use a very simple scalar system to illustrate. Alright, so here is our system. Okay, here's our system in here. And with initial value x of 0 equal to 1. Okay. And now I'm designing an optimal control for the system. The cost function for this system is written as this. So it's a scalar, so really you don't need that vector sign in here. So here is the cost function we're trying to minimize, the quadratic function. Okay. Yeah. And we want to come up with optimal control input to this system for the U. Okay. Now you look at this cost function here, right? It's quadratic format. So the question here that I ask you is, what is the Q value? What is the R value? And what is the S value?
Any positive value?
Based on the given cost function. It's all one, right? Yeah. Okay. So you got to be able to identify that. Okay. Yeah. Now there's another different variation is this. So what I also could give you is this. So J equal to 1/2, starting from 0 here. Okay. So I could also give you like this. Does that make sense? Yes. Perfect. Right? So if I write my cost function like that, basically my last step is incorporating into the summation sign right here. Okay? So in this case here, basically S equal to Q. Excellent, right? Of course, the way I write it here sort of already S equal to, but you could make it a different weighting. You can have a 4 or 5, whatever you want to put it there, right? Yeah. So that's very good. So just make sure if this is written like this, then the last step, this is basically N equal to 10, right? It's the same thing.
So what does changing S and Q do?
When you, I think we talked a little bit about this. When you have a higher value of Q, right? The effect is, if a Q is very high, let's say 100, right? Then you want to minimize the J. Then your only chance to minimize J is to have a much more smaller X, right? So higher Q basically will result in a smaller X value. So the accuracy basically more closer to the 0, right? If you have a very smaller R, let's say 0.1, then you could have a little bit luxury to have a little more control input to the system, right? Yeah. So that's the effect for R and Q involving in time. Okay? But for this question, we're just trying to demonstrate that the algorithm, how it works. Okay. Oh boy. Okay. So yeah. So let's go back to our discrete Riccati equation right here. Okay. I'm gonna choose this one because this one seems there's less writings involved right here, right? I'm gonna choose. Let's see, which one did I choose? I actually choose this one here. Okay, let's choose this one here. So I'm gonna choose that one. P of k equal to Q plus G transpose PK plus 1, and then I plus H R inverse H transpose P of K plus 1 inverse, and then times G. I'll choose this one for my calculation. Okay, so now I'm going to substitute my system information into this equation. Go back to the state equation. Here's your G, here's H, right? So X equal to G times X plus H times U. Okay. And the Q is 1. So basically we got our P of K equal to 1 plus G is 0.368. Here inverse 1 plus 0.632, and then R inverse, which is also already 1, and H transpose, still the same thing, P of K plus 1 inverse and times G. Okay, yeah. So that's what it looks like, right? If you plug in all the numbers. Okay. a little more difficult will be a 2 by 2 matrix, and then you plug in all the matrices, right? Yeah. Okay, so once you get this, and then you can do a simplification at here. So that gives you so I'll give you this one. So now we're ready to solve for these things here. So I'm going to start with P of 10, right? With P10, because of n equal to 10 the last step. And the last step, P equal to S, which is 1. Okay? So then I'll solve for P of 9. Okay? Plugging P of 10 over here, and then here, solve for P of 9. So you get 0.0967. Then you solve for P of 8. You'll get 1.1032. P of 7, 1.1036. P of 6, 1.1037. Okay, so you can keep going. As a matter of fact, you'll notice that after a few steps, this p value, this p matrix set here, will actually basically settle down at this number. Okay, so in other words, basically we're going to set for the rest of them. Basically, it's all going to be actually for the rest of the p of k. It's actually all going to be this much for k equal to 5, 4, 3, 2, 1, and 0. Okay, yeah, and that's your steady state. Basically, this value here is like the p steady state value, okay, for the rest of the k numbers. Okay, so once you get your p, right, once you get your p matrix, then you solve for the gain value k, and the gain value k is over here, right? This is your gain in here. Okay, so we can solve for the gain k. So solve for capital K, okay. From which equation did we see that equation? We said is this is well, we didn't see that any equation here, but anyway. So let's say equation number 10, like this, okay? Yeah. So you can, based on that equation, you can solve for this k now, and then this is a forward solution here. So maybe I'll just write it on here. Okay? So this k at here is equal to R inverse H transpose G transpose inverse P of k minus G. It's the same thing. Yeah. Okay. So this one looks different from this. Basically, if you manipulate this one here, you get the same thing. Okay, you get this k matrix as this one here. So this is same as that equation 9. Okay, same equation 9. Okay, so I'm gonna plug in all the numbers now. So you get k10 equal to 0. Okay, because for the last step, right? This n is last step. Remember, we want our last step. Our last step is 0 there. Okay? And then you solve for k9. Okay, so you get this much out of here. Okay, and then keep going. About maybe at the 6 steps here, okay, and you get basically it's settled down for this gain matrix K. So that's for any other K values. It's the same as this one now. So 5, 4, 3, 2, 1, 0. Okay, for any other steps. So this value here, we call that the steady state gain value at here. Okay, the steady state gain value. So you could now actually look at the response of the system, because you got your k now, and your system is a very simple system like this one here. So your system, you can simulate the system, basically look at, okay, so here's x of k plus 1 equal to, this is my original system. Okay, this is h right here, so negative k times x of k, right? Here's your control input. Okay, control input. And we have our x of 0 given, which is 1. So you plug in x of 0, solve for x1, and then step by step solve for the rest of them, you get the response basically. Okay, yeah. And you'll get the x of 10 basically become a 0. Actually very close. When you're at x of 4, you'll see it's already very close to 0 now. Okay? Yeah. Yes?
So when you pick that k, it's not the final k that you get from it, or is it the varying k for each step?
Yeah, for this one here, you're actually applying the varying k at each step, right? But I'll show you the next one. This is actually in actual implementation. We actually don't use this, because in actual implementation, what we typically treat our system will be an infinite horizon. But we're going to assume we're going to run it for like an infinite number of times.
Right.
Okay. So basically, when you design for optimal control feedback, so for example for this system, you're going to choose this value. Instead of you have a time varying k, you always use a constant k, which is a steady state value k for your implementation.
Okay.
Yeah.
But is that like at k9, or is that like the optimum control k for that?
That's right. Yeah. So, because this is a particular optimal control problem for, let's say, up to, this is n equal to 10 steps, right? So you want to reach a optimal control such that the original g, the cost function g at here, the g at here is minimized. So mathematically, in order for this to be minimized, then you need all of the discrete values at here, right, at each step, so it's minimized basically, right? But when it comes to the actual control, right, what we're looking at is, we're assuming it's an infinite horizon. You know, you have a sampling time 0.01, and you run it for 5 seconds or 10 seconds. That's like infinite number of steps basically, right? Yeah. So we don't need to change our k at each step like this. We can basically choose our steady state, which is what I'm going to cover next. So your k essentially is like this. So it sometimes it start from here and then start from 0, and then settle down basically, right? This is 10 and this is 0, and this is your k at here based on this. Make sense? Yeah. Okay. Okay. So ultimately, in terms of the implementation, right, and nothing really fancy. Basically, the three expressions that are here, okay, for implementation. Okay, that's basically what we're doing in here. Okay. All right. Since now you're saying now, so let's look at basically the next. Next general topic right here. So basically, let's look at the steady state quadratic optimal control. Okay, steady state. Steady state basically means the g, the cost function, okay, will be slightly different now. So because it's a steady state, so the k, right, here, this number of steps goes to infinite. And that's steady state. the steady state, as I said, it's exactly what you're going to implement. If you have a system and here, and then you have your feedback gain, so this gain here is actually taken as a constant. Okay, so k is constant. So that's basically what steady state basically means. Okay. So how do you solve for the k then, right? Actually, we saw that through that example. K will converge after a few steps. Okay. But in terms of the equation-wise, so you see, if we go back to the discrete Riccati equation, right? Discrete Riccati equation. When k is infinite, then both the left side and the right side, they're literally just all infinite now, right? They're all infinite. So your discrete Riccati equation, okay, at n equal to infinite, the p, okay, will equal to q plus c transpose pg minus g transpose p times h and r h p transpose is that r or h? Yeah, P. Yeah. So P H inverse H transpose PG. So both sides take the same value of P now. Okay, same value of P. Okay. Yeah. And then the steady state gain K equal to, you can use this expression right here. So you can use the expression. So how do I solve for this equation? This is basically, this equation here is like a P equal to function of P, right? So P equal to a function of P at here. Yeah. And this kind of equation you can solve with, you can still literally just let P equal to 0 starting from the beginning, and then it will converge to a certain values if you solve for this. Okay. Yeah. And that's how you can solve for this one here. Is that good? Yeah. If you want to use, using MATLAB, and then you have a command basically called DLQR, okay, to actually help you with the calculation for the gain matrix and the P matrix. Okay. Here's my command for DLQR. Yeah.
So you use, when you're implementing, you use steady state K?
That's right.
Process for it?
That's right. So you'll use a steady state value for the K.
Okay.
Yeah. So for example, if you want to use, you can hand calculate this for sure, but you can use MATLAB called the DLQR. Basically give this function your system matrix GH, and also give the Q and R matrices. So this is the Q and R right here, right? And then what this function return, it'll give you back the matrix K and also P at here. And you could also ask for the eigenvalues of the feedback system. So the E at here basically is the eigenvalue of the G minus HK. So the E at here. Okay, it's a vector containing the feedback closed loop poles. Yes?
So I was just wondering, if you're using a steady state K,
Yeah.
would some of your, when you go through the states or the different ends, would some of them you wouldn't be able to predict the value? Because like in the other states you use K that was iterative, and it wasn't always like a constant value out. So if you're using a constant K, would you get different values for this guy?
Yeah, so this is basically not a precisely like the kind of optimal as this finite horizon problem, right? So this finite here is within 10 steps I want to minimize this J at here, right? And then you have to come up with precisely, okay, the P equal to this and the K equal to this to end up with a minimal value for the J function. Okay? But when it comes to the infinite infinite, basically horizon infinite at here. So the first few steps really don't play that much of effect anymore, because typically they will settle down. You see here, they will settle down very quickly after a few steps, right? Yeah. So that minor effect, right, because of this, it shouldn't affect your G that much anymore. You know what I'm saying, right? Yeah. So that's why the infinite here. So infinite meaning really it's infinite, right? But in actual simulation, you can't run it for infinitely. You're running for 10 seconds or I don't know, or right? So we just still consider it as an infinite. So that's not a precise. So it's ultimately the longer you run, then the more precise or more optimal you get for the whole thing, right? Yeah. Does that make sense? Yeah. And which is also like this is not very practical either. You know, you can't every time offline calculate all the key values, right? So. Okay, so that's basically what optimal control is. There's one more thing at here. I think I want to touch upon. Maybe I'll just skip this part at here without the derivation here. Okay, so one more step here. Basically, the question here is, what is the minimum value for GA? Okay, what is the minimum value for the G? So I'm basically kind of stepping back a little bit to my initial value, the initial question here, this GA at here. Okay, so when you have let's say a finite optimal problem at here, okay, with a certain n, we're trying to minimize this whole thing. Well, initially we're trying to minimize the G here, right? And we use the Lagrangian GA. Okay, so the minimum value for the GA will actually be the same as the minimum value for the G, because you see the GA here, you have a system constraint at here, right? And system constraint is 0, so basically the minimum value for the GA will be the same as the minimum value for the G here. So the question for this portion here is, okay, like this kind of question here, right? So you're saying, well, I'm trying to minimize the G here. Then what's the G value, right? What's the minimum G value here? Okay, yeah. So that's what I'm trying to give you the answer here for this portion. So what is the minimum value of the G, A or G? Okay. I'll skip myself some steps that are here, so you can take a look at maybe my lecture notes for this portion at here. Okay. Bottom line is, it's still manipulations of equation 3, equation 1s, okay, to end up with the minimum value here. Okay. I'll write it on the value. So results, okay, for the GA, okay, minimum, okay, or the G minimum, the actual minimum value is 1/2 is this. Okay. So we can derive for the minimum. So we have a solution for the optimal gain K. We have a solution for the P. So we can derive actually what's the actual minimum value for the cost function. And the actual minimum value for the cost function is this one here. So initial condition and initial value for the P matrix at here. Okay, initial value of the P matrix. And your P, always remember, right? Your P of n equal to that S matrix. Okay, and you can solve for the P of 0 using the backward discrete Riccati equation, right? So let's say for that particular example, right? For that particular example, how do we solve for this particular example? Okay, so the same example over here. Okay, for the same example, so P of 0, we end up with what, 1.1037, right? So for this question here, so your J minimum equal to 1/2. Initial value is 1.1037 times 1. Okay. So you end up with 1/2 divided by 2. So you got 0.55, 1, 8, like that. Okay. So that's how you can get your P minimum and the G minimum here. Okay. Now, how you derive here, if you're interested, I'll show you, because I think I'll bore you to death if I do another page of writing here. Okay. Yeah. So now back to the same question in here. Okay. Back to the same question. Now remember, for infinite we have this question here. So I'm going to try that infinite solution in here. So P steady state, okay, equal to 1 plus. Okay, so basically I'm trying this equation in here. Okay. Yeah. And then 1 plus 3.999 PSS infinite. So if I go back a little bit to the function P, okay, so this is my function, original function P here, right? Yeah. And see, this is function P at here. So if I replace both sides with the steady state P, 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 okay? Steady state P, P, P. So what I'm gonna get? And I get this equation here, right? And this is basically a quadratic equation. If you multiply this inverse to the other side, right? Essentially it's like a quadratic equation in here. So that's 1 plus 0.354 PSS over 1 plus 0.3999 PSS, okay, or 0.4. So solve for PSS, and you end up with 1.1037. Same value. Okay. If you use the DLQR, you get the same thing essentially. Okay. That's right. Yeah. So the DLQR give you the steady state value here. Is that good? Yeah. So when you go implement for optimal control, so there are two things you can implement. When you simulate the system, you can simulate the system first. It's negative here. So this is a regulation, right? So this is a regulation type of problem. It's very much just like your pole placement, right? But except that this now your K will be calculated based on the optimal solution, based on a certain set of Q and R. Okay? Yeah. So you give your Q, you give your R, you calculate the K. Okay? Yes. Good point. PSS, yes, needs to be positive. Yes, very good. Yeah. Yeah, actually in this case you do get two solutions. The other solution you get is negative 2.2674. So we get rid. I guess it's not possible. Yeah. See, because this is a scalar, right? But in typical it's a matrix. So the solution that you get for the PSS will be a matrix you get. Yeah. So you're not going to get. I believe it's not going to be all. It's going to be a positive, definite matrix. Yeah, for the P matrix. For the scalar one here, right? See the scalar here? You got a positive and negative. So we pick the positive because this is a negative. So when you get a matrix, you get a. You see, right? Yeah. Okay. So for this portion, just one last note set here. If you're going to design a reference control, okay, if you're going to design a reference control, the approach I would say you do is very much like that reference control for the pole placement. Remember what you do? You insert a K naught, right? And then here is the negative K at here, and here is the system. Okay, so you could calculate your K here just basically the same way as this, and then you can calculate K naught based on the closed loop transfer function, making the DC gains to be 0, to be 1, right? Yeah, to get a K naught here. Okay, so you get a reference control. Is that good? Yeah. And I do have another actually way of reference control for optimal control, but I think I'm going to skip that part. Okay. Yeah. Okay. So I'll see you next week. We'll have a review of probability and we'll look at common filter next week.